Okay, welcome back, and today we're going to discuss the next test, which is the test for independence. And so we're going to use another chi-squared test, and this one is going to have a function on your calculator that everybody should have, whether you have a TI-83 or TI-84. Okay, so I'm going to go through the test with you now, and then we'll do a couple of examples. Okay, so this is the test for independence, which means we're going to be asking the question, are two variables related to each other or not? Is there a significant relationship between two variables, or is there no significant relationship between the two variables? So the independence hypotheses are going to look like this. So we're going to have HO, let me just make sure. Okay, we just want to make sure you can see that. Okay, so we have HO versus HA, so the null versus the alternative. So the null is always going to be that there is no significant relationship. Sorry about that. That there is no significant relationship. And the alternative is going to be that there is a significant relationship. So remember, the null hypothesis is usually always that there is no difference. So in this case, the null is going to be that there is no significant difference or association with the between the two variables. Just hold on one second. Okay, there we go. So there is no significant relationship between whatever variable, this variable and this variable, okay, whatever that turns out to be. Okay, and then of course the alternative hypothesis is going to be that there is a significant, so there is a, and then just the same thing. Okay, so this is one of those hypotheses where you just have to write it all out, and we really can't get around that. But the test statistic that we're going to use is exactly the same test statistic that we used before for the goodness of fit test, except the way we calculate the expected values are going to be different, and we're not going to be dealing with regular tables. We're going to be using contingency tables that we talked about in chapter 3 when we were dealing with conditional probability. So the way we are going to calculate these expected values is going to have a different formula. Okay? And you'll see in a minute. Once I show it to you an example, it'll make complete sense. Okay? So now, the variables, or what we call factors, are either going to be independent or dependent. So if there is no significant relationship between the two variables, then we would say that they are independent. If there is a significant relationship, then we would say that they're dependent. So the null hypothesis is that the variables are independent of each other. The alternative is that they are dependent on each other. So that's another way of phrasing these. Okay. Okay, so let's see here. Let's see, how do I want to do this? Let me do, you know what, let's do an example. That's going to be the best way to do it. And then once I show, because this is no longer going to be a table where we're summing up over a table of values like this, where we have O and E. Well, now we're going to deal with contingency tables that look like this. So we might have something that looks like this, where we have variable 1 or factor 1, and then over here we have variable 2, factor to. Okay. Okay. So now here we have a 2 by 3 matrix, right? We have a contingency table, okay? And so in this case here, we have to look at each of these as a cell, okay? So we're going to have a frequency in each one of these cells. And so we can look at this as cell 11 because it's the first row, first column. It's always row followed by column. So row is always first. So this is the grid. This is the cell, what we call cell. Think of the grid in an Excel file. In an Excel file, you have this big grid where you have rows and columns, and each cell is indicated by a row column coordinate. Okay, so this is the cell that goes with the first row, first column. This would be cell 1-2, which would be first row, second column. This is cell 1-3, which means it's the cell that is in the first row, third column. And then if we go down here, now it's C21, second row, first column, then second row, second column, and then second row, third column. And so that's how we're going to notate the different cells. Okay, now, we're going to have the expected values of these two, right? So in other words, when we do our observed and expected values in a moment, we're going to have a table like this where we're going to have 011, 012, 013, 021, 022, and 023. So we're going to have a table, a matrix, you could say, a matrix or a contingency table of values that are all the observed values that we're going to get. And what we're going to have to do is we're going to have to calculate another table that we're going to call our expected matrix, right? And so what we're going to do is we're going to, based on the data here, we're going to calculate the expected frequency that would go in here. Okay? And then based on the data, we would, and the claim, right, we're going to calculate the expected value that would go in here, and the expected value that would go in here, and of course, down here as well. And so what we're going to end up with is we're going to end up with a matrix of observed values, and then we're going to end up with another matrix with expected values. And so these are the two tables we're going to use in our calculator. And so what we're going to have to do is we're going to have to create a matrix for these values and a matrix for these values in the calculator. So here's the thing. It's very similar to what we did when we create our lists, right? How do we enter our data into the lists? We go to our lists, right? And we go to edit, and we start just entering data into the list, right? Now, what we have to do is we have to go to the matrix menu, and then we have to go to edit and create a matrix for each one of these. So we'll have to create two matrices, okay? Once we create our two matrices, then we can go to the calculator and then just tell the calculator function where our data and our expected values are located. And then it's just, that's it. Okay, so that's the only thing we're going to do. Okay, so now, how do we calculate these expected values? Here's the formula that we're going to use. To calculate the expected value, and I'm going to use E11 as an example. Or let me just use it general. So EIJ. So that means the ith row and the jth column. So what we're going to do is we're going to take the row I, since that's what, so we're going to take the row I total and multiply it by the column J total. And then we're going to multiply it by the grand total. Well, what's the grand total? Remember our chapter 3 and contingency tables? We had our column totals at the bottom, our row totals to the side, and then we had our grand total, which was the total of the entire table frequencies. So that's what's the grand total going to be. So basically, we're going to have our row total, so the observed values, right? So we're going to have our row totals, right? Just like we had before. Over here, we're going to have our column totals. And then right here, right, is going to be the grand total, okay? So we're going to use our data here and these formulas to figure out what should the expected values of the frequencies be, okay? So now, let's use E11 as an example. So E11, we would calculate by saying, okay, we're going to take the first row total, right? So we're going to take row 1 total, and then we're going to take column 1 total, which is down here, and we're going to divide by the grand total. And so what we're going to do is we're going to do that for each one. So as we go from cell to cell, these numbers on top will change depending on what column and row we're in, and then we just divide by the grand total. And then once we do all those calculations, we'll have all of our expected values, and then we're done, okay? And then we just go back, and everything else is the same thing we've done before, okay? So let's do a couple of examples of this. And again, this is a right-tailed test, and remember, our assumptions are also the same. We're talking about random independent samples, okay? And we're also talking about the expected values have to be at least 5. So again, those are the conditions that need to be met, okay, in order to do this test. So now here's the first example. Let me see if there's one here. So the first example says, in a volunteer group, let's see, I just want to make sure. Yeah, in a volunteer group, adults 21 and older volunteer from 1 to 9 hours each week to spend time with a disabled senior citizen. The program recruits among community college students, four-year college students, and non-students. In the following table is a sample of the adult volunteers and the number of hours they volunteer per week. Is the number of hours volunteered independent of the type of volunteer? Which means, does it matter what type of volunteer you are as far as the number of hours that you will end up volunteering for, okay? So our null and alternative hypotheses is we have two things. We have type of volunteer and then the number of hours volunteered, okay? So those are our two variables. So the first one is that there is. So the null is there is no significant relationship between hours worked, or hours volunteered, I should say, hours volunteered and type of volunteer. So in other words, the number of hours volunteered and the type of volunteer are independent. Versus there is a significant relationship between hours volunteered and the type of volunteer, which means dependent. So the null hypothesis is that the hours volunteered and the type of volunteer are independent of each other. The alternative is that they are dependent on each other. Okay? So now, let's see here. And they want to know, are they independent? Okay, well, let's see. 2, we're going to assume the null is true. Assume they are independent. 3, now here's where I'm going to show you how I do it so you don't have to create 2 separate tables. Okay, so the alpha level here is not given. So we are going to assume alpha level 0.05. Now, we know this is going to be a chi-squared test because it's a test for independence. We know that it's going to be a right-tailed test. Okay, so we need to create our expected values and our 2 matrices. The observed values and the expected values. The observed frequencies and the expected frequencies. So here's what I'm going to do. I'm going to create the table. The table is a 3 by 3 table. Okay? So I'm going to create the 3 by 3 table right here. Okay, so here's the table, and over here I'm going to put type of volunteer. So type of volunteer, okay, and so we have community college, 4-year, and non-students. And then the hours worked is going to be 1 to 3 hours per week, 4 to 6 hours per week, and 7 to 9 hours per week. Now, we haven't talked about degrees of freedom. The degrees of freedom here is not the same as the degrees of freedom calculation that we did in the goodness of fit test. Okay, so for this one here, the degrees of freedom is actually calculated by using the number of rows and the number of columns. And so, in general, the degrees of freedom for this type of test, in fact, for the independence test and for the next one, the test for homogeneity, the degrees of freedom are the number of columns, or excuse me, well, it doesn't matter, the number of rows, right, minus 1 times the number of columns minus 1. Okay? So in this case here, we've got a 3 by 3 matrix, so 3 rows, 3 columns. So this is going to be 3 minus 1 times 3 minus 1, which is going to be 2 times 2, which equals 4. So the degrees of freedom in this case will be 4. Okay? So remember, for anytime you're dealing with matrices, where you're dealing with different factors, different variables, and it's going to be the number of columns and the number of rows that are going to tell you the degrees of freedom. And it's the number of rows minus 1 multiplied by the number of columns minus 1. And that's it. So now let's fill in the table. So here's what we have. So 111 fell into this cell, 96 fell here, 48 fell here, 96 fell here, 133, 61, 91, oops. I'm going to rewrite these, and I'll tell you why in a minute. Let me write these first. Okay, so I'm going to rewrite these, and what I'm going to do is I'm going to put a diagonal in each one of these. And so I'm going to put the 111 up here, 96 48, 96, 133, 61, 91, 150, 53. Okay. So those are my observed values. Guess what I'm going to put underneath each one of the diagonals for each cell? That's where I'm going to put the expected values. So let's do the totals. We need our row totals, okay? We need our column totals, and we need our grand total. So here, the row total here, if we add these up, we get a 111, so it'll be 207, $265, and so this is going to be $290, and this is going to be and so the total that I get here is going to be 849. And so if I get, let me just double check that. Always good to double check your work. So let's see. Oops. Clear. Yep, 155, not 165. Okay, and okay. Okay. Okay, so the column totals. So this would be 298. $379. $162. Okay, so now here's the thing. So let's look at this table. So these are the observed values. Now, here's the idea behind the test, okay? If there's no significant relationship between the two variables, in other words, if the two variables are independent of each other, then it shouldn't matter which of the categories of variables or the level of the factors. The distribution across the other factors should be the same. So in this case, regardless of the type of volunteer, the distribution of hours should be the same if they're independent of each other, right? That should make sense from our discussion from Chapter 3 on conditional probability. But that's the idea. Independence means that, hey, there's no relationship between the two. It doesn't matter which type of volunteer you are, the number of hours that those volunteers should all match. So the distribution of frequencies across hours for each type of volunteer should be about the same distribution. Okay? And also vice versa. If we looked at the hours, the type of volunteer that volunteers 1 to 3 hours should be the same as the distribution of the type of volunteers for 4 to 6 hours, and so on. So that's what we mean by independence. And so that's what we're going to be testing. So now what we're going to do is we're going to calculate each one of these expected values. So for this one, E11, okay, we're going to take row 1 total, right? Row 1 total is what? 255 times column 1 total, which is 298, and we're going to multiply those together, and we're going to divide by the grand total, which is 839. Okay? And then E12 is going to be the same thing, except we're going to do row 1 total, which is 255 again, times now column 2 total, which is 379. And we're going to divide by, again, 839, the grand total. And then E13 is this one right here. So we're going to take row 1 total again, because it's in the first row, 255. Now the column 3 total, which is 162. And we're going to divide by 839. And so what we're going to do is now, if I go to the next row, E21, well, now it's going to be the same thing, except now I'm going to 290. So all these 255s change to 290. Everything else stays the same. So it's going to be 290 times 298 over 839. And then E22 is going to be 290 times 379 over 839. And then E23 will equal 290 times 162 over 839. And then finally, the last row, E31, now we're going to use 294, right? So it's going to be 294 times 298 over 839. E32 is going to be 294 times 379 over 839. And then E33 is going to be 294 times 162 over 839. And so if you calculate all of these, which I'm going to do right now, I'm going to just calculate these and put them into the cells. And I would suggest you do the same. Make sure that you get the correct numbers. And I'm going to go out to 1 decimal place. So this is going to be 90.6. And the next one is going to be 115.2. $49.2. Now I'm on to the second row, so it's going to be $103.0. $131.0. 56.0. And now I'm down to the third. So it's going to be 294 times. That's going to be 104.4. $132.8. $56.8. Okay, so now let me double check. Okay, so now that I have this in here, now all I have to do is go to my calculator and put in my two matrices. Okay, so let's do that. So now that I have these matrices all filled in, let's go to the calculator. So I'm going to erase all this. And so here's what I would have on my paper, okay, other than the calculation. I would do all that in my calculator. I wouldn't have this on my paper. I'm doing all that in the calculator. So once I have my numbers filled in, remember, the numbers above these slash marks in each cell is the observed number. The number below the line is the expected number. Okay, and so now how do I figure out my matrices? Well, how do I put them into the calculator? Well, that's what I'm going to show you right now. Okay, so what you're going to want to do is on your calculator, you're going to want to go to this menu, and the way you get to this menu is your matrix menu. So the matrix menu is right, where is it? Right here. Okay, so the matrix menu is right there. See where it says matrix? So you're going to hit second inverse key. So you're going to hit second inverse, and it's going to take you to this menu. Okay, so now this menu, notice that it has names, math, and edit. We want to go to the edit. Okay, so let's go to edit. And now, what we want is we want to choose A. Okay, now all you have to do is hit enter because it's already highlighted. See the cursor? Okay, so now if you go to 1 and hit enter, then all you have to do, now it has a matrix in there that I already created, but we can go ahead and change that. This is a 3 by 3 matrix, so all we have to do is hit the number of rows, which is the first one. So we have the 3 rows, so we're going to hit 3. Okay, so I'm going to hit 3 and then hit enter, and then hit 3 again for the number of columns, and then hit enter. And now what I'm going to do is now it goes straight across. So the way you enter the data is it goes the first cell, then this cell, then this cell, and then it drops to the next row. So it goes by row. So it goes this row, then this row, and then the last row. So that's the way you need to enter the data in. Okay. So that's what I'm going to do, and I'm going to put in the observed values from the table. So these are going to be my observed values. So I'm going to put in 111, 96, 48, 96, 133, 61, 91, 150, 53. Okay, now, there are my numbers. So now I'm done. So now I'm just going to quit out of this. Okay? So if I go to second quit, now, here's the thing. Normally, I would go and put in the second matrix and put in my expected matrix under B. So if I go back to my menu. So I go back to the matrix. I'm going to go to edit. Now normally what I would do is I would go to the edit menu again, right? And then I would choose B, so I'd go down to B. And then what I would do is I would create my B matrix and I would put all of the expected values in here, okay? But what I just learned is that I don't think you don't have to do that. The only thing you have to do is put in your observed matrix. I'm going to test something. So I'm going to delete my matrix. Okay, so hold on a second, let me edit. Hold on a second. Okay, go to edit. Okay, so let me try something. I'm going to go to stat. Okay, so here's what I'm going to do. I'm going to go ahead and create the matrix. And I'm going to see if I get the same answer. Oh, wait a minute. Hold on a second. Hold on a second. Hold on a second. Oh, we did it. Oh, awesome. Okay, so here's the thing. You don't have to do any of the work that I just did. In fact, the calculator calculates all of your expected values for matrix B automatically. Oh my gosh. I didn't know that. I did not know that it did that. Wow, that's awesome. That is awesome. So all you guys need to do is put the data into your one matrix. Oh, that is so cool. So all those calculations I did, you don't have to do. Oh, so that is so cool. Okay, that is so cool. So now, oh, this is going to make it so much easier. So all we need, in fact, I'm just going to erase all of this. Okay, I'm going to put it back in here. So let me redraw this. So let me redraw this. So all you have to do is put the numbers in. So let me put the numbers back in. So here are the numbers. So these are the observed numbers from the data. So I'm just going to put these in here. Okay, so here's where you're at. Okay, in fact, you don't need any of these now. So you don't need any of this. All you need is the table. This is awesome. So all you need is this. So now all you have to do is do exactly what I did. So I'm going to now, I'm going to go back to the menu, right? Now notice, I'm going to show you something. So I'm going to go back to my edit, okay? So here is the A matrix. So I'm going to hit enter. So here's the numbers we just put into A matrix, right? Okay, 3 by 3 matrix, there's all of our numbers. Now, I'm going to go to the B matrix. So here's the B matrix. Nothing's in there, right? That's where I was going to put all of the expected values. Well, guess what? Don't need to do that. So here's what we're going to do. We're going to go on. So now, we're here, right? We know the degrees of freedom, we know this. Well, all we have to do at this point is go to step 4, right? In fact, we don't even need this. But again, don't forget the degrees of freedom. The degrees of freedom in this case is 4. Don't forget, it's the number of rows minus 1 times the number of columns minus 1. You still need to know that. But if you go to step 4 now, once you have this, now with the calculator, you just go to 4, and what we're going to do is we're going to go to our calculator and we're going to use chi-squared test. And the only thing you need to put into your calculator is 2 things. Your A matrix, which is going to have all of your observed values, and then you also need to supply the B matrix, which is going to have all of your expected values. Now, I always thought you had to calculate and create this, but this test, as long as you put in your A matrix, it will automatically create your B matrix and calculate all of the expected values for you automatically. I didn't know that until just now. So now all we have to do is put in our A matrix and it will do the rest for you. And so watch this. I'm going to do the test. So you go under stat tests, scroll up to chi-squared test, hit enter. Now this is what you're going to see, right? So I already have A and B. So we have our A. I didn't create the B matrix. So the observed matrix is A. That's where all the observed values are. B is where the expected values are to be, but we didn't put any in. So now I'm just going to go down to calculate, right? So I'm going to go down to calculate. And I'm going to hit enter. And now look, I get 12.99 for my chi-squared value and 0.0113 for my p-value. So now, I'm going to write that down. So my chi-squared star is 12.99, right? And my p-value is 0.0113. Okay, now I'm going to go back and I'm going to show you something here. Now I'm going to go back to my matrix menu. I'm going to go to edit. Now look at that. Now it says I have a 3 by 3 matrix B. I didn't create one. But if I hit enter, look at that. There are all of the expected values automatically created. That is cool. Okay, so now So now we're off to step 5. So now p-value, which is equal to 0.0113, is that less than alpha? Alpha is 0.05, so that is definitely less than alpha equal to 0.05. So that means, what do? Reject the null hypothesis. Now, step 7. What does that mean for the claim? We're rejecting the null hypothesis, which means there is significant evidence to support that the two variables are dependent. Okay? So, or there's very strong evidence to reject that they are independent. Okay? Depending on what the claim is. Based on the sample data and an alpha level of 0.05. Okay? So let's do another one. I know that was a little haphazard, but I'm so happy I figured that out, that I found that out. So let's do another one, and then that'll wrap it up. So let's see here. So now, let's see here. Let's see here. Okay, so let's do this. So the first thing I want you to do is we're going to use this data, okay? So I want you to use this data here, okay? So go ahead and pause the tape and use this data. We're going to use this data in the next example. I'm not going to write this on the board. So make sure you use this data, okay? So go ahead and pause that and write down this table. Okay, so now, it says the Bureau of Labor Statistics gathers data about employment in the United States. A sample is taken to calculate the number of U.S. citizens working in one of several industry sectors over time. The table that I just showed you shows the results of that sampling. We want to know if the change in the number of jobs is independent of the change in years. State the null and alternative hypothesis and the degrees of freedom. Okay, so as time has progressed every 10 years, so they want to know, has it affected the number of changes in jobs? So do people change jobs more often now or as time goes on? So they have the data from 2000, 2010, and then projected for 2020. So now, using this data, we're going to test whether they're independent or not. So here's the null and alternative. So we're going to say that years, so change in years, and number of job changes are independent. So I'm going to just phrase it the other way. Okay? Versus change in years and number of job changes are dependent. And we want to know if they are independent. So let's say this is the claim. Okay, so now, step 1 is done. Step 2 is we're going to assume, again, the null is true, we're going to assume that they're independent. 3, now, what is alpha level? Alpha level is, they don't tell us, so we're going to use 0.05. Now, what are the degrees of freedom for this table? Well, how many rows do we have? We have 1, 2, 3, 4, 5, 6, 7 sectors. So 7 categories for industry sectors. So that's 7 rows. 1, 2, 3, 4, 5, 6, 7. And we have 3 columns for each year. So the degrees of freedom, remember, is the number of columns minus 1 times the number of rows minus 1. So we have 7 rows, so it's going to be 7 minus 1 times the, and then we have 3 columns, so that's going to be 3 minus 1. So it's going to be this. So it's going to be 6 times 2, which is 12. So the degrees of freedom is going to be 12. Okay. Now, I'm not going to write down the table. Okay, but remember, we have the table for our observed matrix. Okay, so what I'm going to do is I'm going to enter the numbers into the calculator, and then I'm going to go on to step 4 and do the test. And remember, all you have to do is create the one matrix. Okay, so I'm going to go to second inverse to go to my matrix menu, go over to edit, and then hit enter for A. And now I'm going to do it's the number of rows first, so it's a 7 row, so 7 rows. So I'm going to do 7 and then 3 and then enter. Now I'm just going to start entering the data. Remember, enter the data going across each row